And now for something completely different. We're going to end the course with two mini topics. And the first of the two mini topics is the decimal binary octal, and there's one more called hexadecimal. Counting with different kinds of numbers, I guess you might want to call it. So the binary system, that's something everyone's gotta see. I'm going to start with the decimal system though, and by decimal I don't mean 5.6. That's not what I mean. What I mean is deca means 10. What I mean is base 10 counting, which is, we got 10 fingers, so it seems natural to count like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you start over again. 11, 12, 13, 14, and so on. So I always like to think of an odometer, and by an odometer I don't mean those electronic darn things that are everywhere today. I have a thing with electronics. I don't like electronics because electronics hides everything inside of a black box and you can't really see what's going on. In the old days, when you had an odometer on your bicycle or whatever, it had spinning wheels. I loved it. Maybe you have an old enough car or you've seen an old enough car or something where it has wheels. It actually has wheels spinning around. And so if it was a brand new car, you'd have these wheels. There'd probably be more than 4 of them, but whatever. You'd have these wheels that say 0, 0, 0, 0. And then you drive the thing a mile. And what happens? This wheel here is spinning, right? So it spins to a 1. These wheels are not spinning yet. And then it spins to a 2. These wheels are not spinning yet. And then it spins to a 3. These wheels are not spinning yet. And so on, right? So you keep going, 4, 5, 6, 7, 8, 9. Until you get to a 9. And then what happens? Well, now the 9 has to turn around back to a 0, right? But then there's like a little pin on the wheel. There's a pin on this wheel that'll grab this wheel and draw it to a 1. So as the 9 goes to a 0, the 0 goes to a 1. It's the coolest thing to watch. You should get yourself an old-fashioned odometer and watch these things. They're really cool. And so then this 0 keeps going, 1, 2. Meanwhile, all of these dials are still the same, right? This is going to stay as a 1 for a while. Until you get to a 9 again. And then when the 9 turns back to a 0, it has to take this 1 the pin will catch and turn it into a 2, and so on, right? And then eventually you'll get down to, let's say you get down to here, 99, right? This 9 has to go to a 0. The pin catches this wheel, turns it to a 0, and whenever anything turns back to a 0, the pin catches the next wheel over, and so on. So I know you've seen this before, or at least I hope you've seen this before, but it's a really good visual, and there's some fun facts you can get from this. Fun facts about the decimal system, decimal counting system. One fun fact is it's called base 10. Another fun fact, base 10 means 10 faces on each dial. In other words, this dial has a 0, a 1, a 2, a 3, a 4, a 5, a 6, a 7, a 8, a 9. If you count that up, that's 10. That's 10 different faces. So there's 10 faces on each dial. So notice a 10 looks like this. That's a 10. And why is it a 10? Because when you've gone through all 10 faces on this dial and you turn around again, how are you going to show the 10th? You're going to show it this way, as a 1, 0. I mean, you start with the number 0, so 9 is your 10th symbol, but to get to the actual number 10, you're going to need you either need another symbol, which we don't have, or you have to put that wheel back to 0 and drag this one to a 1. So that's what a 10 looks like. And there's another fun fact that I like. Place values. You've heard of place values. Place values go like, what did we call that? We called that the ones place, right? And then, remember, you had to go 10 miles to get to here. And then you'd have to go 20 miles to get to here, right? So that's counting the number of tens. How many times you've gone around 10? How many times this wheel has gone around all its faces? Each time it does, it's 10. So what you're counting is how many tens are there. And then this one, if this one goes 10 times 10, This goes 10 times. If this goes 10 times, that's 10 times 10, which is the hundreds place. And if that goes 10 times, that's 10 times 10 times 10, which is the thousands place. And so on. Hundreds place, thousands place, and so on. And you know how the system works. So the reason I wanted to go through this is now I want to compare and contrast. And I think I might have to shrink this a little bit. Okay, so like I was saying, I wanted to do a binary odometer. Fun facts about binary. Well, it's base 2. That's what binary means, base 2. And so if it's base 2, remember over here we were saying 10 faces, base 10 was 10 faces on each dial. So base 2 is going to be 2 faces on each dial. What are the faces? Just a 0 and a 1. That's all you get. You get a 0 and a 1, that's all you get. So I'm going to start my binary thingy moving here. So that wheel spins to a 1, and you already have to go back to 0. And so this has gone back to 0 means it must have tugged that wheel to a 1. These are still the same. So this is the number 1. That's the number 0. This is the number 1. This is the number 2. And just like I was saying over here, a 10 looks like a 1, 0 because it's base 10. Well, here, a 2 looks like a 1, 0 because it's a 2. Get it? If it's base 10, that's a 10. If it's base 2, that's a 2. Okay, that's something to kind of get. And let's talk about place values now. Actually, let me spin the wheel a little bit more. So this wheel's just going to spin back to a 1, which this will stay a 1, right? But then when this wheel has to go back to 0, it's going to drag this wheel back to 0. And because it went back to 0, that's going to go up to 1 now, right? So notice this is the number 3, this is the number 4. That's what a 4 looks like. If you keep going, basically this wheel keeps spinning. Back and forth, back and forth, back and forth. This one only changes when this 1 goes to a 0, that'll change. When this 1 goes to a 0, that'll change, and so on. So the pattern I like to show is that this is going 0, 1, 0, 1, 0, 1, whereas this wheel is going 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, and then guess what's going on here? 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. So it's kind of cool that way. I like it. Actually, what I don't like is that, because I don't usually count that way, so it's got me all muffed up. So here, that's going to go to a 1. Stay there, stay there, stay there, stay there. Now this 1 has to pull to a 0, which will have to pull this with it, so that 0 becomes a 1. Stay there, stay there. 0 becomes a 1, stay there, stay there, stay there. This 1 has to turn to a 0, which will pull this 1 to a 0, which will pull this 1 to a 0, which will pull this 0 to a 1, and so on. And so what number are we up to now? That's a 4, that's a 5, that's a 6, that's a 7, that's an 8. Suppose I should expand this a little. Oh, sure, why not? That's an 8. So notice, this is the 1's place. This is the 2's place. Again, when we went to a 2, this 1 had to go back to 0 and pull this to a 1. And so that's what a 2 looked like. A 2 looks like this. That is the 2's place. That's always the 1's place, no matter what system you've got. But base 2, that's going to be the 2's place. And then the next one over, remember how it worked before? We had the 10s, and then the 10 times 10s, and then the 10 times 10 times 10s. Well, over here it's kind of doing the same-ish thing. This is the 2 times 2s, otherwise known as the 4s. This is the 2 times 2 times 2s, otherwise known as the 8s. This would be the 16's place, and so on. So a 1 in the 8's place is how we get an 8. Get it? So that's kind of what you got to do to get used to this binary thing, is you got to get used to this idea of an odometer spinning around. Each dial has only two faces, and so you have after the ones place, you have a twos, times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, times 2 is 128, and so on. So you can make the number as big as you want, just your place value is just going to be different. It's all about the place values, really. It's all about the place values. So let's do a couple examples going back and forth between decimal and binary, just to kind of try to get the hang of this a little bit. So you see this little 2 here? This indicates that this is a base 2 number. Okay, because otherwise, if you look at 10110, you might think, what is that, 10,000 something? What is that? And it's like, no, it's not 10,000 something, because it's not written as a decimal number. It's written as a binary number. Our goal is to figure out what the decimal number is. So whoever built this number, it was built by placing into a twos place value system. Let me call that a PVS, place value system. They built this number by plugging into a twos place value system. So that means that, well, that's always the ones, but this is the twos, this is the fours, this is the eights, this would be the 16s, okay? Just like over here. That's how a base 2 place value system works. You get your ones and then your twos. Times 2 is 4. Times 2 is 8s. Times 2 is 16s, and so on. Now a 1, if I have a 1 in the 16s place, it's because I had 16 marbles or whatever, 16 M&Ms or whatever, or the wheel went around, you know, the wheel over here must have gone around at least 16 times to get that 1 to show up. The 1 in the 16s place means I've got 16. Now, if I look at, why does it always erase two things? I don't know. Okay. If you look at this 0 here, which is in the 8s place, it means you've got 0 8s. Or think of the 8 as an 8-pack. You get no 8-packs. You filled up no 8-packs. Well, that gives you nothing. You didn't fill them up. Nothing. You got 0. Nothing. But you do have a 1 in the 4s place. And so now I'm going to have to add on 4. Right? So a 1 in the 16s place, a 1 in the 4s place. Let's see if I can erase this without erasing anything else. Okay, cool. And then notice I've also got a 1 in the 2s place, so that's going to give me 2 more. And then I'm ending with a 0 in the 1s place. So I've got a 0 in the 1s place, means I don't have anything else. So I got a 16, a 4, and a 2. What's this number really? It's a 22. And if you want, you can put the 10 there to emphasize, look, I mean a regular 22. Base 10, decimal counting system, you know, normal. You can put the 10 there to emphasize that, okay? So it turns out 10110 is the binary version of 22. Okay, what I would like you to do is to use what I just did here as a template. Go through the same moves. Take that number, 1101101, which we're told is in the binary system, and make it a decimal number. Go for it. Pause. Pause and come back. Back already? Okay. So again, it's all about place values. This 2 here says, hey, I wrote this using 2's place value system. Using the 2's? Yeah, using the 2's, which means after the 1's place, remember you always start with the 1's place. Don't forget the 1's place. Always start with the 1's place. But after the 1's place, I got a 2's. And after the 2's place is a 4's. And after the 4's place is an 8's. And you keep multiplying by 2 over and over and over. So the next one is 16's. The next one is 32's. And the next one is 64's. So this number goes all the way out to the 64's place. And then you go like this. I've got a 64. And I've got a 1 in the 32's place, which gives me 32 more. And I don't have any 16s, so skip that. But I do have an 8. And I have a 1 in the 4's place, which means I've got a 4. And then I don't have anything in the 2's place, but then I have a 1 in the 1's place, which means one more. So they must have had that many marbles to make it look like a 11011101 in the binary system. So you add this up, 64, 78, 94, 95, 96, 6, 7, 8, 9. Did I do that right? I should check. 109 in the decimal system. 64, 70, 80, 94, 95, 96, 104, 108, 109. Yes, that's right. Cool. Hey, now you can go binary to decimal. Of course, the other thing we should do is we should go the other way, decimal to binary. So maybe I'll get a change of color going. Oh, what's a good color? I didn't get a good color yet. Okay, let's go with this color. What the heck? So this is different, and I find that this is the hardest part for a lot of people. Is they're like, should I do it this way? Where I was, they'll say, oh, binary. They see the word binary, and they say, well, is that the 1s and that's the 2s? And it's like, no, that's not how it works. Why not? Because this is not binary. This has got a 10 on it. This is written with the 10s in mind. So that's the 1's place. That's the 10's place, okay? So that's what that little 10 means. It means that's the 1's place, that's the 10's place. If there was another, it would be the 10 times 10 is 100's place, and so on. So what you want to think, of course, is you say, well, it's 43, right? You don't really have to write this part. You just say, well, it's a normal 43. Maybe that's what I'll write, normal 43. What we want to do is fill in a binary PVS for place value system, which means we want to set up a 1's place, a 2's place, times 2 4's place, times 2 8's place, times 2 16's place. And how do you know how far to go? Well, we got 43, so 16's not enough. I can double it to 32. I could double that to 64, and then you say, well, 43, I don't have enough to fill up a 64, so I don't have to go that far. But I can fill up a 32, and so that's where I should start. And you just think of this as having 43 loose marbles. Think of this as like a bag that'll hold 32. A bag. I'm supposed to talk Minnesotan, right? Bag. A bag that'll hold 32, or a box. Think of a box. It's a 32 pack. It will hold 32 of them suckers. It's going to hold 32 of them suckers. So if I fill it up once, it'll suck up 32 of these suckers. So how many have I got left then? I still got 11 left. See how this works? And now with your 11 left, you come over to the next one and you say, hey, that's a 16 pack. Oh, I don't have enough to fill up a 16 pack. I cannot fill that. And if you can't fill it all the way, just put 0. Come over to the next one. Oh, I got enough to fill an 8 pack. I'm going to fill an 8 pack. 1 8 pack filled up. There we go. And then when I fill up an 8 pack, of course, it's going to suck up 8 of these marbles. So I subtract 8. I still got 3 left. Not enough to fill up a 4 pack, but it is enough to fill up a 2 pack and a 1 pack. And there's your binary number. And if you want to write it out official, you can write it this way. 101011 base 2. What a great answer that is. So notice it's two completely different situations. Here I was reading place 2. This number is place 2. It's been written into place 2 already. I'm trying to decode it. I'm trying to read out. That's the 1s. That's the 2s. That's the 4s. Whereas here, that's the normal number. I'm trying to put it into binary. I'm trying to put it into place 1's place, 2's place, 4's place, 8's place. Okay, so it's two different directions that you might have to go in. So trying to keep that straight, this example, of course, is just like the one above it. We're going to go into the binary, which means we're going to fill in a base 2 system. I invite you to pause and give it a twirl. Having unpaused, we're filling in a binary. So how many places are we going to need? Well, I don't know. Just kind of keep going a little until you get past the 22. So notice when I get to the 32 place, it's like, no, I don't have enough to fill a 32. I don't have enough to fill a 32 pack. So we'll start with the 16s pack. If I got 22 loose cupcakes, sitting around, I can fill up a 16 pack once. So I put the 1 there. And having filled it up once, I still got 6 cupcakes left over. I can't fill up an 8 pack 0 times, so I just put the 0 there. But I can now fill up the 4 pack. And when I fill up the 4 pack once, that'll take 4 of them away. I'll still be left with 2, which means fill up the 2 pack once. And then I'll have none left. And so it's 10110 is the base 2. Okay. Cool. Now, at this point, usually somebody in the class says, what the heck are we ever going to need binary for? And the answer is, let's see if I can remember the right acronym here. I think it's PLCs. PLCs, Programmable Logic Controllers. I think that's what they are. So apparently, if you get a boiler license and you can do the PLCs, you got it made. That's what I've heard anyway. So PLCs, Programmable Logic Controllers, they're the big thing. They're the big thing. Now, if you do want to go that route, then you're going to have to learn Octal too. What the heck is Octal? Octal means base 8. So just think, what are our fun facts for Octal? Well, base 8, 8 symbols on each dial, right? What are the symbols going to be? They're going to have to go from 0 to 7, because that will suck up 8 faces. You put a 0 on one, and a 1 on the next, and a 2 on the next, and a 7 on the last one. That's 8 faces. So Octal, base 8, uses 0 through 7. Well, remember, base 10 uses 0 through 9, and base 2 uses 0 through 1, so base 8 uses 0 through 7. Okay, so it's always like a little bit one less or whatever. So there's going to be 7 faces. What else? An 8, and 8 looks like this. Remember, base 10, that's a 10. Base 2, that's a 2. Base 8, that's an 8. Okay, and the reason that's an 8 is because of the place value system. We'll always start with the ones place, but then we'll have an 8's place. We'll have an 8 times 8 is 64's. Okay, 64 times 8, you'll have a 512's, and so on. So just think of this odometer. Gets down to 007, then it has the 7 pulls to a 0, and it pulls that to a 1, right? So this is a 0, 1, 2, 3, 4, 5, 6, 7. This is an 8. This is what a 9 looks like. And why is that a 9? That's a 9 because you have something in the 8's place and something in the 1's place. An 8 and a 1 makes a 9. Here you've got a 10 because it's an 8 and 2 1's. An 8 and 2 1's makes 10, and so on. So it's this whole place value system. You get down to 077. This pulls to 0, this pulls to 0, this pulls to this. Now by the time you get there, you can do it yourself if you're ambitious, but that will be the number 64. Of course, I can predict that because I know how the place value system works. 1's, 8's, and then 8 times 8. 64. 64 times 8. 512, and so on. Okay, so Octal is very similar. It's just the fun facts are a little different. You have a little different place value. It's got its own place value system. So let's do a couple examples here, why don't we? So I'm going to do example 3a. This is written octal. The little 8 is telling me, hey, I filled in 8 packs, or not 8 packs, but ones. Let me make this a little more clear. I filled in a 1's place, always a 1's place, but then this would be an 8's place, and if I had another one, it would be a 64's place, and so on. To get decimal means what number is this really? Base 10 normal, our normal way of thinking. And so there's a little bit of a difference here, because notice we've got 6 8-packs. That's what this 6 here is telling us. I don't have just one 8-pack. I didn't just fill the 8-pack once. I filled it 6 times. So 6 8-packs is giving me 48. And then in the 1's place, I have not just one 1, I have 2. What do you want to call it, a 1-pack? I don't know what you want to call it. I have a 2 in the 1's place. So that's going to give me 2 more. And so what I've really got is a 50. And you can put a little 10 here to emphasize that's normal. 50 base 10. 50 normal. So a 6-2 in octal, base 8, is the same as a 50. So again, you're going to be doing the same kinds of motions. It's just you got to remember that it goes 1s, 8s, and the thing to really remember is that then it's 64s, right? A lot of people go 1, 8, 16. They want to go from 8 to 16, but that's binary. Binary goes from 8s to 16s. Here's 8s to 64s, to 512s, to 4096s, and so on. I want to come over to this example now, because this is going the other way. Fill in octal. This is the normal number. It has the 10 on it. That's what tells you it's normal. It says, hey, I'm a normal 95. Just a regular, everyday, walking down the street, 95. But I want you to put me in octal packs, so to speak. Put me in an octal place value system. You say, okay, let me set one up for you. We'll start with the 1s place. We'll have to have an 8s place, because that's what octal means, base 8. And then you have to remember this part, right? 8 times 8 is 64, and you have to keep multiplying by 8. 64 times 8, 512. 512 times 8 will be 4096. 4096 times 8. Let's hope we never get that high. Actually, we got 95, right? So we didn't even have to go this high. We don't need those. Let me just erase those. We don't need to go that high. 64 is high enough. And now you have to ask yourself, you have to ask, how many times can I fill up a 64 pack? Well, only once, I guess. But you'd have to think, can I fill it up twice? If I could fill it up twice, I should put a 2 there. If I could fill it up 3 times, I should put a 3 there. Remember, we're allowed to use anything from a 0 to a 7 with octal. So anyway, a 1 is all we got. So you subtract, you say, well, what's left? 95 minus 64, we got 31 left. I still got 31 left. When I fill up one of these 64 packs, I still got 31 loose cupcakes or whatever. So notice that means I could fill the 8 pack more than once. I can fill it 3 times, in fact, because 3 8 packs would suck up 24. So if I suck up 24, let's see what we have. 7. I still got 7 left. And that's good. Remember, it's legal to use anything as high as 7. Please don't put 8s or 9s in here. It's not, if you put 8s or 9s, you should back up because you need to refill, because you should only use 0s to 7s. Anyway, I got 7 loose ones, which I could put in the 1 place. And so there it is. A 137 base 8 is the same as a 95, normal 95 base 10. Okay, so I did the one example going each way. So now it's your turn. Notice these are both, they look like 35s on the face of it, but this is a normal 35, but this is a 35 that's actually not a 35. It's a 3-5. 3-5 base 8. It's a 3-5 octal. So make this octal into decimal, make this decimal into octal. Pause that tape and give it a tour. Having come back, let's see what I get here. Okay, I want normal. I want decimal means I want normal. Or another way to say it, this 8 here is telling me that this is the 8's place. If I had another place, it would be the 64s and so on. Okay, the little 8 is telling me that this number was coded into place value 8s, 1s, 8s, and so on. So notice I've got 3 8 packs filled up. 3 8 packs means I got 24. I got 5, I don't know if you want to call it a 1 pack, but I will. 5 1 packs gives you 5. And so this is the number 29 normally. 3 5 and base 8 is what we normally think of as a 29. Let's try this one. Now this is base 10. This really is a 35. As we normally think of numbers, that's a 35. But we're trying to write it as an octal number, which means we're trying to write it as a base 8 number. Now notice, we don't have to use that many decimal places, right? It's only 35. I'm not going to be able to fill up a 64. So since I can't fill up a 64, I might as well just erase that and start from here. So I got 35. I can fill up an 8 pack 4 times. 4 times 8 will suck up 32 of these things. So I got 3 left, and so I got 3 left. Put the 3 in the ones place. And so 43 base 8 is the same as a normal 35.